of what we discussed is we are discussing CTC algorithm for speech recognition. Primarily, it is used for speech recognition, but it could be used for any sequence classification task. The paper which I am using, this is the paper by Alex Graves and others. You can get this paper online. I have also shared it in the shared folder. So I would strongly recommend that read this paper. It is very well written and you will understand many things there. Um, I gave an example. What is the problem about? It is you have an audio file and you have the corresponding text. What is there in the audio file? Typically, this audio file is of the order of 10 to 20 seconds, not more than that. Huh? It's not like 1 hour of audio. It's only 10 to 20 seconds of audio and then corresponding text is there. But you don't know the segments. Where is hello starting? Where is what? Where is, where is your, where is name? You only know the order in which these words are being spoken. That's it, right? You don't know exact segments, but only the order. That's it. Now, that's the problem at hand. We want to train a machine learning model, which is mostly an RNN, recurrent neural network, to do this modeling. Input is the audio or audio features, and output is the text or the sentence. And now we have input is, we discussed this. It could be audio frames, m-dimensional vector, MFCC or LFBE, log filter bank energies. All those features are possible. And then your X is basically a sequence of frames. That's your input. And your target output is a string, let's say. It could be made up of any basic units. These basic units are from some vocabulary. You can take it as characters. Let's say every character, 26 characters in English, let's say. So these are your basic units and you plus blank, okay, well, sorry, space bar, that is also there. So 27 you can assume, 27 characters and then you just use them to write your sentences. Or it could be words. You have, let's say, I'm telling you my telephone number is 543-645 something. So the basic units are these words, right? The 1, 2, 3. These are your basic units in that case. Or you can take the entire dictionary, which may have, let's say, 1 million words, and you can take them as your basic units. Any possibility is there. Or it could be even word pieces. Let's say I say running. You can say ing is one word piece, and run maybe r is one, un is one, ing is one. So just some subword units, they can make your basic vocabulary. And then using this vocabulary, you are constructing sentences. Basically, the output of your neural networks, it's a softmax layer, right? Classification problem, softmax layer, and the output layer neurons correspond to these units of the vocabulary, right? Clear? Easy? And so your Z is also a sequence of these units, and the length of this sequence will be less than or equal to the length of your audio, capital T, right? Which is obvious because every frame will map to only one, and because of deduplication, you may have lesser length. Okay, now the task is to train a temporal classifier, right? That's clear. I will just skip this part, it was discussed earlier. The distance or the error measure is edit distance, right? The ground truth sentence is this, and my predicted sentence is this. What is the edit distance? Substitutions, insertions, deletions. That is what is the metric for evaluation. Now the model is, I will skip these details. The model is simply an RNN, and we discussed about the notion of path. We make something called a trellis, and we find a path in that trellis, right? And we discussed this. I will leave it. And we discuss the B operator. What does it do? Deduplication and then blank removal. Removes the consecutive duplicates and then removes the blanks. And we saw some examples here, and both of them will map to AAB. We discussed the mathematical notion of this path. I will quickly skip this part. During inference, let's say you have trained a model. If you have received a trained model, how do you use it for ASR task? So the answer is first get your YTs. What are YTs? These are the activations of your final layer of your RNN, those YTs you got. Then find the best path in that YTs. That is one method, best path decoding. But a more proper way to do it is, or more rigorous way to do it is, find which word, because one word can correspond to multiple paths, right? I'm saying cap, I can say, let's say here, if I use, it could be CCAAPP, it could be CCCAPP, or blanks also in between. Okay, in this case, blanks are not there. So all these are valid paths, right? So every possible word output can correspond to multiple paths. So ideally, we should sum over all those paths and find the probability of that word. And we should do this for all the possible words, right? And then whichever word gets the highest probability, that word should be selected as the output, right? And that method is called prefix beam search, means there is an efficient algorithm to do it. Because this is a sequential task, you can use dynamic programming to simplify this task. So that's what we do. Both methods are used, but prefix beam search is more accurate than best path decoding. All of you are with me? Because we discussed this at length in the last class, so I'm not discussing all the details again. So yeah, that's what we discussed. And then we quickly had a detour to what is dynamic programming, right? So we started with one simple problem. It could be edit distance or aligning two stretch time series, or basically to find the best alignment between two different strings, let's say. And we discussed, first we find the element-wise cost. We construct a matrix like this. This is like our trellis. And then we find the best path in the trellis given the path constraints. Like not all paths are allowed. You can't jump here and there. Some path constraints are there. For example, in this case, it is move from one node down, or move one node right, or move diagonally, but you can't jump over nodes. In this example, you can define your own constraints. So on the optimal path, basically you use this Bellman's optimality condition where you recursively find or dynamically find the solution. Let's say the best path, I will just use this example. The best path, let's say if you start from this corner, the best path to come here is this path. Then you find the best path to come here is either from here or from here or from here. Take only the best one out of these three possibilities. In this way, you keep expanding all the way to the end point. Let's say the end point is here in this case, for example. Then whatever path reaches this point with the least cost or the maximum score, that path you choose. So that's a very efficient algorithm to find the best path. Uh, and it's a dynamic programming based algorithm. So then I summarized what is dynamic programming. So you want to reach from one point to other point given some movement constraints. So you basically keep optimizing, start from the starting point and keep growing. And finally, when you hit the target point, so find the best, means trace back the best path. That's it. Okay, that was all done in the last class. Now we are going to do not the inference, but the training. Okay, now you know if I give you a trained model, how you will use it to find the inference or the output. Right? If I give you the trained model, I give you some audio, now you know how to find the output sentence. Now the question is, okay, now how do you train this model? I gave you the data, audio and the corresponding text and multiple files or multiple pairs. Now you want to train the model. So that's a big challenge. You have already read this in the HMM literature. In HMMs also you have solved similar problem and you train the model in some way. So we'll be using very similar methods here, but I'll be discussing one algorithm which maybe we didn't discuss in HMMs, forward backward algorithm. We didn't discuss in HMMs, right? Okay, no problem. So we will discuss this algorithm here. The same algorithm applies to HMMs also. Very nice algorithm, and you will see the Beautiful form. Okay. Now, whenever you train a model, what is the first thing you do? First, you define a loss function or an objective function. What is the loss function or objective function in this case? What objective function can we use? It's the maximum likelihood. What all loss functions do you know? Huh? Cross entropy. Cross entropy can be derived from maximum likelihood or KL divergence minimization. So yes, that is a loss function. What else do you know? Map estimator, maximum a posteriori estimator. What else do you know? Huh? Mean squared error, very good. That is used for regression problems. Mean squared error. So these are very commonly used loss functions. Hmm? So we are using in this case ML loss function, maximum likelihood objective. We want to maximize the likelihood of the true word given the audio and the parameters. NW are the network parameters. NW is the network with parameters W, right? We want to maximize this probability on our training data. That's how we train it. All right. So uh, basically, you're writing it in terms of W now. What is your W? W is that value of W, or call it W star, let's say. W star is that W which maximizes this loss function, which is maximum likelihood loss. In other words, it is simply you are given the XZ pairs from your training data and log of PZ given X. That's what we have here, PZ given X. Here we have given theta also or NW also. For brevity, brevity means for, because I'm lazy and don't want to write same thing over and over again, I will not be writing here NW, but it is, you can assume that wherever you see P, NW is kind of are the parameters. Hmm? Okay, so is this clear, this sentence? This is simply the Monte Carlo estimate of your loss function, right? You had your log P, you take an expectation value over log P, that is maximum likelihood estimate, and this is the Monte Carlo estimate. Given the samples, how do you estimate that quantity? Expected value of log P. Just take summation over log P. Okay, so that's your W, huh? So to find, so basically you have to minimize this loss function. Okay, so instead of maximizing this term, you can minimize the negative of this term. Same thing, but just the paper uses a negative sign, and that's because they want to minimize some loss function. So just a formality. Now the question is, what is the value of W? How will you find the value of W which minimizes this loss function or OW? Differentiate with respect to W and then put it equal to 0. Now your W is such a complicated network, RNN network. Can you make your derivative equal to 0? It won't happen. Then what will you do? Gradient descent. So whenever your objective function is not analytically solvable, you use numerical techniques, and here the numerical technique is gradient descent algorithm. And for gradient descent, what do we need? Gradient of, very good, of the loss function or the objective function with respect to the parameters. So you need this. This is the formula for gradient descent. All of you agree? The W is updated as the previous value of W minus eta times the gradient at the previous value of W, right? So what is the unknown here? You know W, you know eta. Eta is a learning rate. You can fix it, or there are algorithms which tell you what is the learning rate we can use. Now the quantity which we don't know is gradient of OW with respect to W. What is gradient of OW with respect to W? You can use chain rule and say gradient of O with respect to Y. Y is the model output, the activation of model output, and derivative of Y with respect to W. Out of these two quantities, one quantity you already know. Which one is that? Gradient of output with respect to parameters. How do you know that? From RNN literature. In RNN, you know how to find the gradients of the output with respect to the network parameters, right? You use some backpropagation through time algorithm, right? And if it is not an LSTM or if it is not a recurrent network, if it is a dense network, then also you know what is gradient of output with respect to parameters, right? You have studied the neural network theory. You know how to compute the gradient of output with respect to the parameters. So only term which we don't know is the first term, gradient of O with respect to Y, right? This gradient of O with respect to Y, and O is basically minus log P Z given X, and with respect to Y. This is what we want to find. Here lies the whole now focus. How to compute? First of all, how to compute Pz given X? We want to compute Pz given X in a form which is easy to differentiate with respect to W or with respect to Yk, output Y, right? I want to find this quantity Pz given X in a form such that it is easy to differentiate with respect to Yk, Ytk, the model output. So now we will assume some notations. Feel free to write them down in your notebook. Let's say L is any text sequence. And this L can be set as Z while training. When Z is given to you, you can say L is my Z. So this, let's say L is any output sequence, text sequence. So we'll work with Z, we'll work with L in general, and then while training, just substitute L with Z. Then that becomes your, during training, the value of L. So we want to find P of L given X, right? What is the probability of any label sequence given the audio input? So maths is a bit involved here. We will take help of an example. So throughout this class, we will use this example. Let's say I said a word pass, right? And my L is, let's say, the sequence of characters PASS, right? This is my example. So my L is PASS, 4 characters. And my input is the audio pass. All right. Now, first of all, from L, we will construct L dash. What is L dash? It's the blank inserted version of L. What is that? Dash P dash A dash S dash S dash. So this is the thing. If I apply operator B on this, I will get back L, right? Now take care that these two S's, they will not be merged. Because first we do deduplication, then blank removal, right? If I don't put a blank in between these two S's, then they will be merged into single S. So the blank helps keep the double letters separate. Clear? Okay. We will use this small s to index L dash. So what is L dash 1? Blank. What is L dash of L dash 2? P. L dash 3 is again blank, like that. Okay. Now the question is, wake up question. What is the length of L dash in terms of length of L? So mod L dash is basically length of L dash. And what is it in terms of mod L? Yes, 2L plus 1. Very good. Now, to help you further understand this thing, let's plot it. Let's plot this thing, the trellis T versus S. It's something like this. So you can see here S. This is S equal to 1, blank. S equal to 2 is P. S equal to 3 is again blank, like that, PASS with blanks. And this is the T, time. You want to align your audio input, which is in the columns, with the text output, which is in the rows. Right? Or let's say x-axis is T and y-axis is S. Right? You want to find the best path. Is this clear? Okay. Tell me from this. So what are these things. What is a node here? It is basically the YTK, the output of your neural network. At time t, what is the probability of P? What is the probability of A, S, all that 26 characters plus a space plus a blank, 28 total. So YTK. Here there is no K, I'm using S. Okay. So what is PL given X? Write down in your notebook. We have done this before, so just recap. From this trellis, what is P of L, this label sequence, given the X? From X we computed this YTK. You can use your notes. You have previous class notes. Feel free to look through them. Anybody done? Uh, it's a bit involved. So think so that you can enter the concepts. What is P of L given X? Okay. Okay. Anybody done? Just raise your hand. If not, then I will answer. Yeah. So basically, your output will be pass. Your output will be this PASS. If you take any of those valid paths which lead to pass, right? There are multiple outputs which will give you the same output pass. So probability of pass is basically sum over all those paths, sum over all those trajectories which you take, which end up in pass, which means you apply the B operator on that trajectory. If you get a pass, that is a valid trajectory, and then you sum over all such trajectories. That's your total probability of getting pass given X. So P of L given X is basically sum over all the trajectories. Pi is a trajectory, a valid trajectory, which with all the transition constraints. Uh, P pi given X is one trajectory. Sum over all those paths whose B is equal to L, right? Clear? Now tell me what is P pi given X? So what is P pi given X? What is the probability of one path? Product of all the y terms in that path, right? I hope you remember this. Very good. So product over all the y terms which fall on that path. So ytk. Here k is basically pi t. Pi t means the character which appears at time t in the path pi. For example, if my path is, let's take an example, let's say I go from 1 to 3, let's say diagonal path we can take just for example. Then at t equal to 2, my pi t, my pi t is p. My pi of 2 is equal to p. So this output will be ytp. It means the output of my neural network at t equal to 2, which corresponds to the p neuron. Right? Every neuron is a character, right? Let's say. So the neuron which corresponds to character p, what is their output? That is y2p. Notation is clear. Don't make a mistake in notation. It's okay. Done. Easy, right? So far, good. Now what do we need? We need derivative of log of p L given x with respect to y tk. That's what we need now, huh? We know what is p L given x. Now, how do we differentiate it with respect to y tk? So, in other words, intuitively thinking, let's say ytk is some neuron. Maybe let's say at t equal to 2, my my k is p. Let's say at t equal to 2, k equal to p, I'm interested in this neuron, huh? I'm interested in this neuron. Now, when you differentiate this p L given x with respect to the output of this neuron, what will that be equal to? So first of all, in p L given x, there are so many paths possible. Only those paths will appear which pass through this neuron, right? Paths can be formed by multiple paths, but derivative of other paths will be equal to 0. Only those paths will appear where this neuron is a part of the path, right? So basically, we have to only find those paths, valid paths, or those paths which lead to PASS. So only those paths which pass through this neuron, and then differentiate their sum with respect to YK. Okay, now let's do it properly now. So basically I'm saying all paths that pass through the node ytk. So let us consider all the valid paths. Okay. So we need all the paths which pass through this neuron, huh? So we'll break the problem into two parts. On the left side, we will take all the paths, valid paths, which end up in this neuron. On the right hand side, we will take all the valid paths which start from this neuron. It's like this neuron becomes like a bottleneck, huh? All the paths have to pass through this neuron. Only then the derivative will be non-zero. Otherwise, derivative is 0. So this neuron is my bottleneck here. So all the paths which converge or which end up in yk, and then next part is all the paths which start from yk. So let's alpha. Yeah, note it down if it helps you. Then note it. Beta also I show. Okay, this is beta. All paths starting at this node and basically sum over all the paths. You are summing over all s. I will sum over all s. No, but it by p a corresponds to not all s. You fix your a. Let's say you are p. Then summation. Summation will be there or will not there. Will be some different form. What is that a? A is p, let's say capital P. Or k could be capital S. Right? Think about it. Will it stand? And this summation goes what? All else. So what is YKT? YKT means you are at time t and you have k is let's say a capital P. K corresponds to whatever let's say capital P. Will you get all S or because k is specified some Yes, okay, I will now. So I am happy that many students they tried it very well. So let's see where we are. Okay, so we are here. How to compute this term, and this term is written here. Now the question is, how do we compute it? So let's see what is there. Uh, Alpha is summation of many paths, beta is summation of many paths. When you multiply them, basically it gives you all possible paths. It's all paths like this path and that path, and product over all those yt's along that path. That is one term, and then you add over the other path, second, next path, etc. What is the derivative of this PL given x with respect to y tk? Let's say t is 2 or 3, let's say in this case, and a is, sorry, k is capital A. Right? K is some neuron, and let's say that neuron corresponds to capital A. Hmm? So now, uh, look at one path. Let's say this path. Let's say 1, 2, 3, 4, 5. In this term, what is it? This is y of this into y of this into y of this into y of this into y of this. When you differentiate this product with respect to this y, what do you get? Huh? All the rest of the y's, right? So what is this product term? It's basically, look at one addendum here, or what one term which is getting summed. It is this y into this y into this y into this y into this y, and you're differentiating it with respect to this y. So it's this linear term. That y that disappears, and whatever remains, that remains. So you just divide by yk square. There is no need to do division rule, because in the numerator there is only one yt l dash s, right? So that's what you will get. Okay. If L dash S is not equal to K, which means I'm looking at, this is my L dash S, but my K is somewhere here, then that derivative will become 0. Derivative will not appear. Alpha, beta are, no, they are not constant. They are a linear function of ytk. Alpha into beta, you have a linear term with ytk, plus over other paths again a linear term, plus over another path and again a linear term. So it's linear with ytk. That's why the derivative, simply you just remove that linear term and the coefficient is the derivative. That's why we square the denominator. Yes, yes, yeah. And beta is linear. Yeah, that's also same logic. Okay, now the question is, why do we have a summation here? Summation is here because it is possible that the same character k, let's say k is capital S, Take the example when k is capital S. It is appearing twice, which means if you fix your t, let's say my t is 3, let's assume my t is 3. Now this term ytk will be, same ytk will be here and same ytk will be here. The neural network just says the output of the probability of S is this much. Probability of the capital S given the input audio is this much. Now, whether it is this capital S or this capital S, that depends on the path. That is not given by the neural network, right? So therefore, we do summation over all uh, neurons or all S which correspond to capital S. That's what we are adding, no? No, no, no. Neural network is fixed. It has only single S in the output. Only one neuron corresponds to capital S. Right? Now that S could be this S or that S. That depends on trellis. Both could be valid. Therefore, we sum over both. Right. So, in other words, I'll put it in another words. So, all paths which pass through this neuron, their derivative will be non-zero, and all paths passing through this neuron, their derivative will also be non-zero. That's why we added up both their derivatives. Right? Easy? Okay, if you understood this, then that's alpha beta algorithm. That's done. So now you know how to differentiate your loss function or likelihood function with respect to output of the neural network. That's it, done. And you use it basically in your algorithm, and it is able to learn. So you get all the technologies which you use today. It is built on this algorithm. Easy, right? Good. Um, Now I will do some. Now you may say alpha and beta are very difficult to compute. Huh? To compute alpha, you have to find all the paths which end up in this neuron. To compute beta, all the paths which start from this neuron. That is very difficult to compute. So now I'll present a recursive algorithm or dynamic programming based algorithm which can very efficiently compute alpha and beta. Ultimately, alpha and beta is all what you need. The gradients are composed of alphas and betas. How do you compute alphas and betas very efficiently? That's what we will discuss now. Let's look at alpha. This is dynamic programming. Dynamic programming means you compute the value of alpha at one place where it is easiest to compute. From there you compute next alpha which depends on this, just like you did it in beta B algorithm or the best part decoding algorithm, right? You computed your loss at one end and then you gradually propagated it and then computed over all the nodes and you reached the final node and traced back the best path. Right? So it was dynamic programming algorithm. Similarly, we'll do dynamic programming to compute alphas. So tell me now, what is the value of alpha? I've given the expression on the top. Tell me the value of alpha at the green node. Means alpha t equal to 1, s equal to 1. What is the value of alpha? T equal to 1, s equal to 1. Y, y1, y11. What is y11? Y1 is, okay, time is 1. What is second one? Dash, yes, a blank. So L1 is always blank. Or L dash 1 is always a blank. So L dash 1. So you initialize it first. So what is alpha t equal to 1, s equal to 1? That is y at t equal to 1 and your k is basically blank. And what is alpha at t equal to 1, s equal to 2? Huh? Pardon? Y 1p, yes. And p is basically L dash of 2 or L of 1, either of them. Huh? So L dash of 2 or L of 1. Good. So you're able to initialize it. What about s equal to 3? It's not a valid path. Then probability is 0. Very good. So probability is 0 because none of these paths, any path which starts from here or here or here, they're not valid paths. So their probabilities are 0. Probability of getting a PASS from those paths is 0, in other words, right? So it is 0 for all s greater than 2. Done. Now let's come to recursion. So you found the value of alpha at t equal to 1 for all the nodes. At t equal to 1, you are able to find. Now, what is the value of alpha at t equal to 2 and 3 and 4? You can compute by recursively applying this formula or with dynamic programming. So let's do that. So in general, so I will consider t minus 1, t plus 1. And let's say I end up in this. What is the probability of, so I'm using recursion. So what is the alpha ts? Let's say at this node, huh? What is alpha ts at this node? The allowed transitions are given with the arrows. any valid path which reaches here can either come from this node or this node or this node, right? You can either get A repeated, so this node, or dash A or PA. All three are valid paths. So tell me what is alpha ST. If you know values of alpha at this layer, at t minus 1, if you know, what is the value of alpha at this layer? Let's say at this node. Very good. Very good. So you got here alpha at t minus 1th layer at the sth node, like s is 4 in this case, sth node plus this path which is at s minus 1th node plus this path which is s minus 2th node. So you multiply this with y, right? You're multiplying y's right along the path. So just take all those paths and they end up here and you multiply with y. That's it. Easy. Very good. I'm coming there. You are one step ahead. Good. Okay. Recursion. Okay. Now tell me in this example. Now you have a blank here. Huh? You have a blank here. What is the alpha st at this node if you know alpha st minus 1 at all the nodes here? What is this alpha st at this node? S minus 2 node should not appear because the transition from blank to blank is not allowed because you will skip the p altogether. It won't be a valid path. So this, if L dash S is a blank, means this is a blank, then basically this path is not allowed. Right? So what do you get then? Only two terms at sth node and the s minus 1th node. That's it. And you multiply it with the current y, ytl dash s. That's it. Now, what about repetition? You have s, then s, PASS. So, what is alpha TS if L dash S is equal to L dash S minus 2? Or in other words, if um, L of that, whatever, S by 2, S by 2, right, is equal to L of S by 2 minus 1. Yeah, again, this path will not be allowed. This path, you cannot jump from one S to the next S because then they will be deduplicated to become single S. But we want double S, so blank must be there. So you want to come from here to here, then come via the blank. This path is not allowed. Come via blank or come via this S. All right. So we have now handled all three possibilities. Now let's summarize this. So in summary, you get this basically. If it's a repetition or if your current node is a blank, then only two paths are allowed. Otherwise, in general case, all three paths are allowed. And then you can, in a recursive way, dynamic programming way, you can compute the alphas in linear time. All right. Now, a tricky question, simple question, but you may think, what is PL given X in terms of alpha TS alone? If you know all the alphas, do you know PL given X? You know all alphas. What is PL given X? Think about it. It's very easy. Just do it. Are you sure? If you take all the T's, then those paths may not be valid. No? Very good. Yes, I think many of you are able to think that. Right? So when I say PASS, my at capital T, my last time, it should end up in either capital S or it should end up in this blank. Both are valid paths. All other paths will not be valid. Huh? So what is P then? P is the sum of those alphas. That's it. So alpha T at, oh, I think it should be capital T, not small t. Sorry, small type. So it is alpha capital T at L dash plus alpha capital T at L dash minus 1. So the mod of L dash minus 1. All right, that's it. Same thing you can do with now beta. Now you understood everything actually. There is nothing difficult here. Beta is given in this way. Now you are going backwards. Huh? So which beta is the easiest to compute? At t equal to 1 or t equal to capital T? T equal to capital T. The last ones are the easiest to compute. So what do you get there? So initialize. What is beta at capital T when S is the last, like the length of the L dash? Here it is 9. Huh? What is the beta here? What is the beta here? Y t at S is equal to 9. Huh? Okay, good. So it is S equal to 9 is blank basically. So Y at t equal to capital T and your output is blank. That is your beta at this node. Now what is the beta at this node? It is beta capital T S equal to L dash length minus 1. This one. Huh? Yeah, YT of capital S, which is basically uh, the string, the last element of the string L, or the second last element of the expanded string L dash. And what is at this node at S minus S equal to L dash minus 2? Are you sure? Because no valid path will end up here. So probability is 0. So it is 0 for all the S which are less than L dash minus 1. All right. Now again recursion. So now tell me what is beta TS? What is beta TS? If you know beta T plus 1S, you know all these beta T plus 1. What is beta T now at this node, let's say? Anybody is done? Raise your hand. Okay. What's your name? Om. Okay. Yeah. Yeah, very good. So basically you take this path, multiply it with yt L dash S, which is the output here or the softmax output at this node, and take this path, multiply with y, take this path, multiply with y. So sum over all three, that is your beta. Right? This is the general case. Now let's look at the special cases where we have some problem. One problem appears when it is a blank, when your current node is a blank node. So what do? You basically don't allow this jump. And your beta becomes only sum of two paths multiplied by the current node. Clear? Okay, now if L dash S is repeated, then what do? Let's say in this case SS, you know beta at T plus 1. What is the beta at T here? Let's say at this node. Ignore this jump. You can't jump from S to S without a blank. So this is ignored, huh? And your beta is basically then sum over two paths only. Yeah, and then you can make a general beta, right? Your beta is basically sum over two paths if it is same repeated character or a blank, and sum over three paths otherwise. Again, uh, teaser, what is PL given X in terms of beta TS alone? So you have a beta 1 at s equal to 1. So you can end up either in this blank or this P. You can't end up in any other node. So you sum over these two quantities. That is total probability. Done? Okay. A quick question. Why don't you use this expression to differentiate? It's complicated, huh? So you can't find gradients from this expression. Although this is a valid expression, but difficult to differentiate. Other expression was easy to differentiate. Okay, that's why we need all the alphas, all the betas, and then combine them to find the derivatives. Good, all clear. Now this algorithm is called the CTC forward backward algorithm because we're finding the forward paths and backward paths, and that helps us to find the gradients. And after you train the network, this figure is from the paper directly. So look at this one, the bottommost row. After you train with the CTC loss function, your outputs are like this. Let's say this is the time axis. On the x-axis is the time axis. When you say then you won't get the sound everywhere. Means your model will not output the for all the sounds. It will output only for a few neurons or for a few time steps. It's a recursive network, right? It has a memory. So let's look at this one, huh? Let's say you say sound. So sound. This sound, the model will not output the everywhere wherever is active. It will only output somewhere in the middle or somewhere towards the end. Because it's a recursive network, it has a memory. So it will keep like silent and then suddenly it will say, oh yeah, it was an And then again it will become silent. So when I say silent, it's like inserting those blanks. So when it is silent means it is outputting only blanks. So it is like blank, 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 then blank, 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 then blank, 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 then blank, 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 etc. And then when you apply B operator on it, then you get THE space SOUND space OF like that. Right? Okay. Now this was the theory. If you want to do practical implementation, there is a very good library by NVIDIA. NVIDIA is the company who makes GPUs, right? And they've been working very uh, aggressively on speech recognition and other speech tasks. So they have made a library, publicly available library called Nemo. It's available online, open to all. You can use its codes, modify it. Everything is open source. And then you have tutorials again from NVIDIA, and this code basically implements CTC from scratch. It's very simple, very clean codes. You don't have to write all those algorithms on your own because everything is packaged nicely in this library. So you can just use it. Use it for your project. So if you are doing a project on ASR or something other speech related task, you can use this library. It's very useful. And also one more thing, don't train the models from scratch. There are pre-trained models available. Find whichever pre-trained model suits best for your task. Just pick it up and start using it. Fine tune it. Fine tuning means train it on your limited data. But these models are generally trained on like thousands of hours of data. So it's not worth doing that again yourself. We don't have even that many resources here. NVIDIA is the company can make as many chips, but we have limited resources. So generally what people do is they just take those models and then they fine tune them for their task. And it works very well. It gives you the advantage of all that previous data also, which you don't have, but NVIDIA has trained it on. Okay. There are some projects in which people use these codes and train the whole model from scratch on their own data. but then they have to have so many resources, like thousands of hours of data and so many GPU resources. For example, when people want to train something on some new language, let's say uh, Punjabi, then you can train a pre-trained, you can take a pre-trained model, let's say in English or Indian languages or whatever is available, and then you start training it on Punjabi, and that's how you. But then again, you need lots of data because uh, it may have to learn many things which other languages may not have, right? So again, finding a similar pre-trained model is will help. If I am training something for Punjabi, but I'm using English, versus if I want to train a Punjabi model and I use Hindi or Dogri or Urdu, that will be much better, right? English is quite far from Punjabi, but these languages are much closer to Punjabi, so maybe model can learn better like that. So these are some common tricks, hands-on tricks for real implementations. Anybody has any questions? So in CTC, your input has to be, let's say, those chunked versions. You basically give some xt, where t is window number. So now what is your input? You can give some feature vector, or you can give the entire audio in that window as an input. It's up to you. Both uh, people have tried with both. But of course, when you're giving complete audio as an input, computational load increases. But if you directly use some features, then model can be much smaller. Another problem which may come if you are using directly the audio is what's your sampling rate. If you change your sampling rate, then information may stretch, or then just make sure that you fix a sampling rate, and whatever audio you are giving, you use that sampling rate only. Yeah. It's a standard number, but you can define whatever you want. All right. For our projects, yeah. Um, Something with speech, or something with audio, something with music. I can tell you